Okay, so now let's look at the next worksheet. So the first question. A car has mass 650 kilograms. The driver of the car has mass 70 kilograms. And for the first part, we don't need this information. We're just looking to state Newton's third law. Then determine the combined weight of the car and driver. Assuming that the weight of the car and the driver is evenly distributed, determine the normal reaction force exerted by the ground on each tyre. Okay, so let's have a look at this now. Okay. So 650 kg and 70 kg. So we'll just write that down here. $650 kg, and then the driver or the person, that was 70 kg. Okay, so part 1 was state Newton's third law. So Newton's third law basically says for every action, there is an equal and opposite reaction. So maybe put some letters in here. For every action, let's say, call the action A, there is a reaction, I'll call it OR, and the idea here is that the size of A is also equal to the size of OR, and that the sign is just opposite. So for every action, there is an equal and opposite reaction. Okay, part 2 now. Part 2 was just calculate the combined mass, so that's straightforward. 720 kg. And then part 3 was calculate the reaction on each tyre. So here's the car here. And what's happened here now, you have 4 tyres. And each tyre is in contact with the ground, but it's not going through the ground, so it must be because the ground is pushing back, so each tyre feels a reaction force here. And because it's perfectly balanced, the reaction force on each tyre will be exactly the same. Now, it's not moving vertically, so the total upward force, which is 4R here, that must equal the total downward force, which in this case here is just gravity is the only downward force. So the only force you have down here is 720 times G newtons. So we basically get this equation to solve for OR. So OR will be 720 times G divided by 4. So we get the calculator out again. Just a second. Okay, there we go. 720 times 9.81 divided by 4 I get, or the reaction force will be 1766 newtons. That'll be the reaction force. Okay, that ends the first part, so let's have a look at the next part of the question. Next part. When starting from rest, the car has an initial acceleration of 3.5 meters per second squared. Determine the magnitude of the driving force delivered by the engine. If the driving force of the engine is delivered through the two front wheels of the car, determine the magnitude and direction of the total reaction force that the ground exerts on each of the front tires when the car is initially accelerating. Okay, so 3.5 now is really what we need from this. So the next part. Okay. B part. So we have the car now, and it's accelerating, and the acceleration here is 3.5 meters per second squared. So we want to calculate the force. So F equals ma. So F equals 720, which is the mass, times the acceleration. So I get the driving force will equal 720 times 3.5. That would be 2520 newtons. And now the last part, there's our tire, and the driving force is delivered through the two front tires. So what will happen is that each tire will exert a force of exactly half of this, since the total driving force will be split between the two front tires. So that's 2,520 divided by 2, so that's 1260 newtons. And let's not forget, we also have the reaction force acting on the tire, which we calculated earlier as 1766 newtons. Let's see now, what exactly are we asked for now in this part? If the driving force of the engine is delivered through the two front wheels of the car, determine the magnitude and direction of the total reaction force that the ground exerts on each of the front tires when the car is initially accelerating. Okay. So, what's happening here is that because the tire is in contact with the ground, it's able to drive forwards with this driving force, and of course because the tire is in contact with the ground, it's being prevented from falling down due to gravity. So you have the ground providing two reactions, this vertical one here stopping it from falling vertically, and because of friction and the tire being in contact with the ground, it's allowed to drive forwards. So this is also a sort of reaction as well. In fact, it's a reaction of, or result of, the tire spinning clockwise and creating friction between the ground. If you just look for a moment, the tire, if you put a little dot on the tire, as the tire spins, the dot would move this way around the tire. So when you look down below here, the dot is moving to the left. So the rubber of the tire is moving to the left, which means the friction force between the tire and the ground will be to the right. So in fact this here is caused by friction between the rubber and the tarmac of the ground. So there's the two reaction forces, and we just want to add these together, so that's no problem for us here. So the total reaction force will be 1260 horizontally plus 1766 vertically. So the magnitude of this, that would be the square root of this squared plus this squared. So let's see, 1260 squared plus 1766 squared, and then square root that, and you get 2169 newtons. So when you add these two together, you get a vector this way of 2169 newtons. And the formula I used, if you remember, the magnitude of a vector is just square root x squared plus y squared. And we also need to calculate the angle here, theta. So we use the formula tan inverse y over x is equal to theta. So I can just about squeeze it in here. Theta will equal tan inverse y over x, so 1766 divided by 1260, and then tan inverse that, and that will be 54.5 degrees. Okay, and that ends that question now. So let's have a look at the next question. So question 2. A train and an engine has total mass of 2.5 times 10 to the 6 kg. It's at rest in a station. The engine of the train begins to exert a force of 700 kilonewtons, causing the train engine to accelerate uniformly until it reaches a velocity of 56 meters per second. Assuming that the force from the engine remains constant and that no resistive forces act, determine the acceleration, that's the A, the time taken to reach this velocity, that's the T, and the S here. So this really is like a UVATS problem, but requires the use of F equals ma as well. So let's have a look here. So it's 2.5 times 10 to the 6. So 2.5 million kg and 700,000 newtons. So 2.5 times 10 to the 6 kg. That is the mass, and the force is 700,000, so that's 7 times 10 to the 5 newtons. And then using our F equals ma formula, F equals ma, we get A must equal F over m. F over m. Let's calculate this now. So that will be 2.8 times 10 to the minus 1. So that will be equal to 0.28 meters per second squared. And that's the A. We also want the T, and I think it was to reach a velocity of 56. Yeah, 56 meters per second. So we have, as part 2, U equals 0, V equals 56, A equals 0.28, and we want the T, so V equals U plus AT will do it. V equals U plus AT. So Calculating now. 56 divided by 0.28. So that's a nice exact answer of 200 seconds. And the last part now is to calculate the S. So maybe we can use S equals UT plus a half A T squared. So I get S equals 0.14 times 40,000. So that's 5,600 meters. Well, let's have a look at the next question. Okay, so we have here, diagram shows a climber of mass 75.5 kg here, suspended from two ropes tied at A and B, and the angles are 40 and 50. The system's in equilibrium, so that's important. All the forces cancel. Write the equations for the resolved forces vertically, the resolved forces horizontally, and then calculate the tensions. Okay, so here, this here would be T1 cos 40, because this part is adjacent to the angle. And then this one here, that's T1 sine 40. And then the other way, that will be T2. Now there's the 50, so this one will be sine 50. And then this one here, that will be T2 cos 50. So there are the two upward forces. That's the force left, that's the force right. And then we also have a downward force here of 75.5 G. Okay. So that really answers the horizontal and vertical parts. There's all the forces there. So we can calculate, well, we can't actually calculate them because we don't know what T1 or T2 is. So I don't see much point in getting the cos 40 and cos 50 yet. But now the second part is to calculate T1 and T2. So what you have here, the total up force, T1 cos 40. Let's try that again. T1 cos 40 plus T2 cos 50. That needs to equal 75.5 G. That's the total upward force. That must equal the total downward force. And then the total leftwards force must equal the total to the right. So we have two equations and two unknowns, T1 and T2, and we can solve. So you could do this using matrices if we like, or we can just put the numbers in. I think I'll just slightly rearrange the second equation. So let's get the numbers. Cos 40, let's see what we have for cos 40. Okay, so we get cos 40 T1 plus cos 50 T2 equals 75.5. No, that won't fit. We'll have to write this down. Okay. So it was cos 40 T1 plus cos 50 T2 equals 75.5 G. And then on the second equation, we have T1 sine 40 equals T2 sine 50. So sine 40 T1 minus sine 50 T2, that needs to equal 0. So in matrix form, T1, T2, that will equal the inverse of cos 40 cos 50 sine 40 minus sine 50, 75.5 G and 0 inverse. So that equals 1 over determinant. So 1 over minus here, minus cos 40 sine 50 and then minus cos 50 sine 40. And then we swap, so that's minus sine 50 cos 40 minus cos 50 minus sine 40, and then multiply. Okay, so let's have a look here now. 40 cos multiplied by 50 sine. So that would be minus 0.5868, and then cos 50 sine 40, cos 50 times sine 40. That'd be also minus 0.4131. So together that would be minus 1, so that's actually quite nice. Okay, so that minus can actually go inside, so we can get rid of lots of minus signs now, which is better. So now I have sine 50 cos 50 sine 40 cos 40 times 75.5 G and 0. Okay, so T1, T2 will equal this row by this column. So that would be 75.5 G sine 50. And then this row by this column, that'd be 75.5 G sine 40. So let's calculate them now. So that would be 567 newtons. And T2 will be 476 newtons. Question 4 now. A large steel ball of mass 200 kg is suspended from a steel cable. A horizontal force F is applied so that the cable makes an angle theta to the vertical as shown. In this position, the tension T in the cable has a magnitude of 2,300 newtons. So this is 2,300 newtons this way. The weight is 200 G this way. The F we don't know. And we are looking for probably the F. The weight, the F and the theta. Okay. this theta. Let's finish the triangle here. This t here can be broken up into a force this way and a force this way. That's 90 there. Now, this side here is the side opposite theta, so this one is the sine. And so this one must be the cos. So, what can we say? Well, the left force equals the right force, assuming it's in equilibrium. In fact, we're not told this in the question, but unfortunately I think they meant to say that, or they didn't make it clear. Again, anyways, assuming that the left force equals the right force, we don't get anything helpful there because we don't know Fn, we don't know theta, but assuming that the up force equals the down force, we can get the theta out. Let me actually calculate this exactly. So 200 times 9.81. So that would be 1962. So that is the total weight. I think that was part 1. And that needs to equal 2300 cos theta. So we can get the theta out of that, no problem. Divide by 2300 and then cos inverse, and theta must be 31.5 degrees. Therefore theta equals 31.5 degrees. So now we can find the f, because here the f must equal this, left equals right. So you get f must equal 2300 sine 31.5. So the f will equal exactly, nearly, actually, 1200 newtons. And that answers that question. For me, it seemed a little bit more natural to get the weight first, then the theta, then the force. I think we've seen this previously before, where actually answering the parts of the question out of order is sometimes easier than how they're actually asked, or at least more natural. Okay, last question now, question 5. A golf ball of mass 0.045 kg is struck by a golf club so that the ball has an initial velocity of 41 meters per second and an angle to 37 degrees to the horizontal. During the stroke, the club was in contact with the ball for 6 times 10 to the minus 3 seconds. Determine the magnitude of the average force that the golf club exerted on the golf ball during the stroke. So what's happened here now? There's the golf ball, and it's being struck, and it's launched off at an angle here, initially at rest, and then launched off at 41 meters per second in this little setup here. So it goes from rest to 41 meters per second in this amount of time. So we can calculate the acceleration for when the golf club was in contact with the golf ball. So we have u equals 0, v equals 41, and t equals 6 times 10 to the minus 3. So I believe v equals u plus at. U is 0, so I get v equals at. So I get a is just v over t. So a is just v over t. Now I just did something quick in my head there. 1 over 10 to the minus 3 is the same thing as 10 to the positive 3. Now that's just something quick there. 6.8333 times 10 to the 3. So we get here 6833. Now that might seem like a very, very high acceleration, and it is a very high acceleration, and it's that high because it's only accelerating with that acceleration for a very short amount of time. So for the time velocity graph, what you have here, if you want to picture it, the ball's at rest and then it's struck, and then the ball leaves the golf club and then travels off at a constant velocity, at least for near the beginning. So the acceleration, the slope at the beginning is very, very steep because it's only in contact for a very small amount of time, and it needs to go from 0 to 41 meters per second. Okay, by reference to an appropriate law of motion, state the magnitude of the average force exerted on the golf club by the ball. So we have the acceleration, we have the mass, so we can calculate the force. F equals ma. This is Newton's second law. Newton's second law. F equals ma. So that will be 0.045 times the a we just found. So that would be 0.045, 307.5. So if we go for 3 significant figures, that would be 308 newtons. Determine the time taken for the golf ball to reach its maximum vertical height. So the ball is launched across the golf course at an angle 37, 41 meters per second. So that's 41 cos 37. And then this part here is 41 sine 37. And we want the maximum height, so we've seen this before. That's when Vy equals 0. So V is U plus AT. AT, that needs to equal 0. So solving this, we get get the calculator out here. .52 seconds to reach its maximum height. Assuming that the golf course is completely horizontal, determine the distance along the course that the golf ball travels before it hits the ground. So that's the range. So the range is again Sx at the time of flight. Now, in this diagram here, you know it takes 2.52 seconds to reach the maximum height. This is completely symmetric, this setup here. The time taken to go from here to here is the same as from here to here. So in fact, the time of flight is just going to be double the time to the maximum height. So 5.03 seconds. In other words, I just saved myself the trouble of solving this equation. I didn't need to do that. I just had to double this number. So it was a little shortcut I took there. So that would be U T and then plus a half AT squared, but there's no A, so it's just going to be those two terms multiplied, which I get as an answer of 165 meters is the range. 37 cos times 41 times 5.3. Yeah. Okay, and that ends that part, the question. So some of these questions, you see, I felt they were short enough that you could almost do them on the question page themselves. Some of the questions, like here, I suppose if you write small enough, you could do it on the page, but you need to really do it in your notebook. And then question 2 here, I had plenty of space. I suppose I could have done that on the page. And question 1, I definitely had to do that in the notebook. Okay, you might want to double check all my calculations in number 5 here. Only because the numbers at the end seem a little bit small. Now it could be correct, but 2.52 seconds to reach the maximum height, I suppose, is okay. But 165 meters range, that's not particularly far range. I suppose this would make sense if the golfer was pitching a short distance rather than teeing off from the green. But just double check my calculations in the last part. Might have something slightly off, but you never know.